For this video, we're going to cover graphing rational functions. Now, this graphing section is going to be a lot different than our other sections. We are not going to be using a parent function to do transformations. Having said that, it's going to be really useful to know what the parent function is. Now, everything I'm going to talk about in this video is summarized here. So first, let's talk a little bit about what a rational function is and what the parent function looks like. So the parent function for a rational function is going to be f of x is equal to 1 over x. So this is the simplest rational function you can have. And the big idea with a rational function is it's a function that's written as a fraction and has a variable in the denominator. Now 1 over x is going to have two asymptotes. It's going to have a vertical at x equals 0. So VA, vertical asymptote, at x equals 0. And then it's going to have a horizontal asymptote. So let's say HA, horizontal asymptote, at y equals 0. And then the function looks like this. So I have a curve here and a curve here. So remember, the curve approaches the asymptote. So we're not going to do transformations, like I said. We're going to have some steps we're going to use to graph any rational function. But you can see that finding out where the asymptotes are is going to be really important. And that's usually going to be the first thing we find and the first thing we draw. So let's start talking about a horizontal asymptote, because that's usually going to be the most complicated, the most difficult part to find. Now, in general, we're going to use this for identifying parts to use for the horizontal asymptote. So instead of the parent function like this, we're going to write something in general that's going to look like this. So we're going to have some coefficient a x to the n plus stuff. Now that stuff could be anything. It could be variables. But when we are looking for the horizontal asymptote, the only things we care about is the leading coefficient and the exponent. Same for the denominator. Plus stuff. Again, that could be a lot of different stuff. It could be more complicated. But for looking for the horizontal asymptote, again, we only care about leading coefficient and exponent. Now, to find the horizontal asymptote, the first thing we need to do is compare n and m. We need to compare the values for our exponents. So there's three things that can happen. So for one, n could be smaller than n. So the degree could be bigger on the bottom. Whenever the degree on the bottom is larger, the horizontal asymptote is at y equals 0. Now, another possibility, n could be larger than m, so the degree could be bigger on top. Now, in this case, we would actually have what's called a slant asymptote, but that's not something we're going to cover until pre-calc. So I think for the most part, you shouldn't run into problems where the degree is bigger on top. If it does happen, for our purposes, we're just going to say there's no horizontal asymptote, because we're not going to deal with slant asymptotes until later. So last possibility, n could be equal to m. The exponent in the top and bottom, the degree could be the same. When the degree is the same, the horizontal asymptote is at y equals a over b. So the leading coefficients tell us where the horizontal asymptote is. All right, let's do some practice just finding the horizontal asymptote. Then we'll do a couple examples graphing a full rational function. Again, everything I just talked about is summarized here. Okay, so for the first one, remember if a degree is not written, it's 1. So that's first degree, that's first degree. So in this case, the degree is the same. When the degree is the same, our horizontal asymptote is at y equals a over b, right? The leading coefficients. In this case, that's 2 over 1. Again, when a number's not written in front, we say it's 1. Or we can say it's y equals 2. Here, again, we have second degree, so again, the degree is the same. So our asymptote is at y equals a over b, in this case, 2 over 3. So our horizontal asymptote is at 2/3. Again, when the degree is not written, it's 1. So here the degree is larger on the bottom. When the degree is larger on the bottom, your horizontal asymptote is at y equals 0. All right, next. In some cases, you will see that our rational function has already been factored. So we do need to think about what would it be if we distributed. this case, x times x is x squared. Another way to say it is first degree makes a second degree. On the bottom, we only have a first degree. So in this case, the degree would be larger on the top. When the degree is larger on the top, for now we're going to say no horizontal asymptote. We will deal with the slant asymptotes later. Last one. So first degree. So top and bottom are going to be a second degree. So the degree is the same. So our horizontal asymptote will be at y equals a over b, our leading coefficients. When the numerator and denominator are fully factored, these values out front are the leading coefficients. So this would be 6 over 3, or you could say y is 2. All right, so let's do a couple full examples. And again, all the steps I talk about are summarized at the top. So first, we're going to find the vertical asymptote. So VA, vertical asymptote. Now, to find the vertical asymptote, we want to set the denominator equal to 0. And the reason is our vertical asymptote happens when the denominator is 0. The idea is, remember, we can't divide by 0. So we want to exclude that value. So that's where our asymptote's going to be. So set the denominator equal to 0. Our denominator is x minus 4. Solve for x. So x is going to be 4. So that's our vertical asymptote. Now, a hole in the graph occurs when you are canceling factors. In this example, there's no canceling, so we're going to have no holes. Horizontal asymptote. So on the bottom, it's a first degree. On the top, we do not have a variable. When there is no variable, we can say it's degree 0. So in this case, our degree is bigger on the bottom. When the degree is bigger on the bottom, our horizontal asymptote is at y equals 0. All right, x-intercept. Now for the x-intercept, let's do a little bit of an aside. We'll talk about the x-intercept a little bit. Because usually with an x-intercept, you would just set y equal to 0. Now, that will still work, but we can kind of cheat a little bit. So let's think about something, say, like y equals x plus 2 over 7, or sorry, x plus 2 over x minus 7. Now we could set y equal to 0, solve for x, but we can use that we know 0 divided by anything, almost anything, so 0 divided by 2 is equal to 0. So as long as our numerator is 0, this entire thing will be 0. So another way to say it is 0 over x minus 7. 0 divided by a number is 0. So as long as your numerator is 0, you will get 0. So we could also just say, well, when is x plus 2 equal to 0? When is the numerator equal to 0? When x is negative 2. So for our x-intercept, we have two options. We can set the numerator equal to 0, or set y equal to 0. Most of the time, it's going to be a lot easier to just make the numerator 0. Now, there is one complication. For this example, there's no variables in the numerator. We can't set the numerator equal to 0 because it has a value of 2. So if there's no x in the numerator, that means there's no x-intercept. Y-intercept works just like y-intercepts in the past. So if we're looking for our y-intercept, we're going to set x to 0. And then plug it into our equation. So say y is equal to 2 over 0 minus 4, or 2 over minus 4, which is minus 1/2. Now, whenever we're writing our x and y intercepts, it's a good idea to write it as a coordinate. So for our y-intercept, x was 0, and then we found y is minus 1/2. Now, for our domain and range, we could do the domain and range right now. For this problem, let's draw it first, talk about why the domain and range is the way it is. Next time, we'll go ahead and put them in first. So always a good idea to draw your vertical asymptote, horizontal asymptote first. So our vertical is at x equals 4. Horizontal, y equals 0. So no x-intercept, but we can put in our y-intercept. So 0 minus 1/2, so it's right there. Now, we can draw this part. Remember, it's going to be a curve. Make sure it goes through your intercept and it approaches your asymptotes. make sure it doesn't cross your asymptote. Now, we could draw the curve here. We know there's going to be a curve approaching our asymptotes. When you are drawing a curve on a side that you do not have a point for, there's no intercept, you need to find at least one point. So choose an x value, plug into the original, find at least one point you can draw your curve through. So it looks like x equals 5 might be a good value to choose. So when x is 5, y is going to be 2. So over 5, up 2, about right there. So now I can draw my curve. Okay, last bit, domain and range. So remember, the domain is a description of all x values that we can have. So left and right. So you can see going left, I can go to negative infinity. Going right, I can go to every value except that x equals 5. And then every value except, sorry, x equals 4. Every value except x equals 4. From there, I can go to positive infinity. So there's really only one x value we can't have. So for domain, we're just going to say it could be all real values except x cannot be 4. So the domain is everything except our vertical asymptote. Range, we're going to do the same way. Right? You can go up to infinity, you can go down to negative infinity. The only value we cannot have is where our asymptote is. So we can have all real numbers except y cannot be 0. All right, let's go through one more example, follow all the same steps. All right, vertical asymptote, set the denominator to 0. So denominator is x plus 5. So I'm going to say, okay, when is x plus 5 equal to 0? When x is minus 5. So vertical asymptote at x equals negative 5. Again, a hole occurs when we are able to cancel factors. Nothing here we can cancel, none. Horizontal asymptote. So we're going to start by looking at the degree. Top is a first degree, bottom is a first degree. So the degree is the same. When the degree is the same, our horizontal asymptote is at y equals a over b, our leading coefficients. So in this case, it's going to be 2 over 1 or 2. So horizontal asymptote is at y equals 2. So x-intercept, where we can set the numerator to 0. In this case, that's going to work nicely. So say when is 2x minus 1 equal to 0? add 1 to both sides. So when is 2x equal to 1, divide both sides by 2. So x is 1/2. So our x is 1/2. Our y is going to be 0. So our x-intercept happens when y is 0. All right, y-intercept. So we want to make x equal to 0, plug it into our original. So y is equal to 2 times 0 minus 1 over 0 plus 5. Or minus 1 over 5. So when x was 0, y was negative 1/5. Now we can just go ahead and put our domain and range in now. All right, so our domain is going to be all real numbers except where our vertical asymptote is. So all values except x cannot be negative 5. Our range is going to be all real except where our horizontal asymptote is. So y values cannot be 2. All right, let's start with our asymptotes. So vertical at x equals negative 5. Horizontal, y equals 2. Put in our intercepts. So x is 1/2 0, it's about right there. And then when x is 0, y is negative 1/5. Get as close as we can. It's hard to see, so it's about right there. So x is 1/2, y is minus 1/5. About the best you can do is negative 1/2. So we can put in our curve on this side. Just make sure you go through your points and approach your asymptotes. And then again, we do not have a point on this side, so we want to choose an x value to find at least one point. It looks like minus 6 probably good. Negative 13 over minus 1 is going to be 13. So when x is negative 6, we go up 13. So about right here. Draw your curve, make sure you go through your point and approach your asymptote. Done.